This talk's called High Availability and Fault Tolerance. My name's Mark Miller. A little bit about who I am. I'm a Lucene junkie from back in about 2006, Solar committer in 2009, et cetera, et cetera. I've been doing Lucene and Solar pretty much my whole career other than the first couple years, although even then I started working pretty heavily with Lucene very early. So I've been doing this a long time. I've done a variety of core Lucene work. I worked a lot on some of the per segment stuff way back in the day that got us towards near real-time search, along with a lot of bug fixing. In the past 5 or 6 years, I've done a lot more Solar core work, as well as co-creating the initial SolrCloud code with Yannick Seeley. So this talk is a little bit about how SolrCloud tries to protect your data and handle automatic fault tolerance. And a few things that still need to change. A lot of the fault tolerance design and code is still very close to the original, and that leaves a few things to be desired still. So I'm going to kind of talk a little bit about how the current fault tolerance setup works. I'm not going to go into super low detail. I'm going to try to get some detail. There's really not enough time to talk about every little corner, but I'm going to try to get an overview of kind of how things work and some of the limitations around that, as well as some of the work going on to fix that. So SolrCloud, this is the diagram I made way back on probably one of my first talks and put it at the top of the SolrCloud wiki page. It still pretty much applies. There hasn't been any major architectural changes. When Yannick and I first talked about making SolrCloud, we looked at a variety of systems and in terms of what distributed system we wanted to base our fault tolerance model on. Overall, it really came down to kind of two choices, kind of a Cassandra type model where any node is pretty much always available for writes, but you can end up with a lot of eventual consistency issues because if any node is available for writes, that means one node can be partitioned from the rest of your cluster except a write, and later on when that node reconnects to the cluster, you've got to reconcile the fact that updates to the same documents could have happened in different places. So that was kind of the first model we looked at because there's a great Dynamo paper by Amazon that really explains all the details of that and how to do all the hashing on a ring, et cetera. At the end of the day, we ended up going with a different model that focuses more on consistency and is not as eventually consistent. It makes things, from a search engine perspective, we decided it just fit better. It's a lot easier to do certain things like optimistic concurrency, which is something we really wanted to do for some NoSQL type features. So basically what that means is you end up with a fairly simple system where you shard the index. And so when a document comes in, you can hash on its ID, determine what shard it goes to. From that point, you can kind of treat each shard individually in terms of fault tolerance and replication. Each one is kind of a self-contained slice of the index, and they don't really have to cross-communicate to deal with fault tolerance or anything. So the basic idea is you shard the index, and then for each shard, you can also add a replica. And the replica will act as one fault tolerance. It's another copy of your index, as well as expanding capacity. It's another machine that can serve queries. So you're sharded and you're replicated. That was kind of the simple idea. This was basically, Solar worked in a distributed mode before SolrCloud, but you could do distributed search. You had master-slave replication, where you could set up a master and replicate the index to slaves and expand for query throughput. But it was pretty much all on you to do the work. You had to hash and partition the data yourself. You had to set up all of the replication to happen with configuration. It wasn't like all automatic. If one of your nodes went down, the system attempted to repair it. So we had kind of a distributed system that was kind of do it yourself. Our goal was to add on the smarts so that stuff kind of started happening automatically. So the other part of it is we wanted to deal with things like configuration in a better manner. There's kind of a couple ways you can deal with configuration. The Hadoop world tends to deal with it where every single node has its own local configuration, and some sort of management tool tries to ensure that that configuration on each node is in sync. We went with a different route where we were using Apache Zookeeper, and it turned out to be an okay place to store configuration files in a central location so that all the nodes can look at one place, and you don't have the possibility of differing configs on different nodes. Zookeeper also gave us the ability to do things like leader election and kind of just cluster coordination in a way that we didn't have to deal with a lot of distributed problems. We could count on Zookeeper to have already handled a lot of that for us. So the failure cases, that's pretty much the setup. We did the search side of that way back in like 2009, 2010, where we plugged in Zookeeper. We wouldn't, if you index data, it was still up to you to hash and distribute the data. It was still up to you to deal with failure cases, but the initial SolrCloud code that we put out allowed it so that each node could register in Zookeeper. So when you were doing distributed search, rather than having to specify all of the nodes your search was going to go across, it could look at Zookeeper and do that automatically. A couple years later, like 2011, 2012, we did most of the work on the update side, where we start distributing the updates for you, we do the hashing for you, and we do the automatic recovery for you. So as we're thinking about what we have to handle for automatic failover and recovery, there's really only a few cases in our kind of sharded replicated system. One of them, the more complicated case, is that a leader dies. Like while you're indexing, a leader dies. It could have been sending documents to its replicas. When it dies, maybe it sent an update to one replica but not another. So now you have an inconsistent state, and you have to deal with that. Another case is if a replica dies. So you've got documents coming into a leader of a shard, and it has to distribute those documents to the replica. One of the replicas may just go away. That's kind of an easier case. You just kind of have to handle when the replica comes back, it has to get back into sync with the leader. And then another case is a replica is partitioned. And because we use Zookeeper, you can have odd partitions in the system. We kind of punted on this early, but now we have a better system for it. So you could have like the leader can talk, or the leader can't talk to a replica, but both of them can talk to Zookeeper. Because we use Zookeeper to coordinate the cluster, if both of them can talk to Zookeepers, the cluster thinks both of those nodes are good. But meanwhile, there may be a partition where the leader can't speak to the replica, so it's not good. So we kind of have to deal with those odd partitioning cases. So the more simple case is the replica recovery. There's a couple cases where this has to happen. On cluster startup, we want to elect a leader for a shard, and we don't know when you start up if that shard is in sync. There may be a replica that's out of date that someone fixed that machine and brought it back into the mix. And so when you start up, you have to run through all of this kind of recovery process to make sure that some old replica didn't come in and become the leader and erase a lot of your data. You also have to do this replica recovery process if in a live indexing system, a replica goes down and then comes back. And the way that we consider a replica going down is when a solar core starts up, which is a solar core is an approximation of one replica, it's got one index. It registers itself in Zookeeper, and it uses what's called an ephemeral node in Zookeeper, which has like a heartbeat with the Zookeeper client. If that heartbeat dies, if the node goes down, if garbage collection takes too long and the machine can't talk to the Zookeeper quorum in a long enough time, then that ephemeral node in Zookeeper goes away. We consider that node down. So that'll happen if you stop the node. That'll happen if the node can't communicate with the network anymore, if the node gets under load and can't communicate in the network fast enough. All of those things will cause a Zookeeper disconnect. We consider that the replica died. When the Zookeeper will automatically try to reconnect in the background, or if the machine is dead, maybe the machine gets restarted, and then it will recreate that ephemeral node, and now that replica has to sync back up with the shard and make sure that it has all the latest data. So kind of here's kind of the process of how that works. So let's say you have a shard, you have a leader, you have a bunch of replicas, somebody's indexing data. That data gets hashed to that shard, comes into the leader. The leader will actually version the document so that when it's sending the documents to the replica, it's actually sending them not in like a straight queue. It will send them as it gets them. And so you can end up with cases where someone's doing updates to the same document, and an update may beat the original document from the leader to a replica. So the leader will version all of those documents to ensure that on each replica, the latest update wins. But so when the replica comes back, in order to sync up, this is kind of the process we have. This all happens in a class called recovery strategy. I tried to encapsulate most of this recovery stuff into simple spots, so it's easy to look. The leader recovery stuff happens in something called sync strategy. The replica recovery stuff happens in something called recovery strategy. So one of the things we added to SolrCloud to make all this work is a transaction log. We added that for a few reasons. One is single node durability. The way Lucene works, if a machine crashes, Lucene is built so that it's not supposed to ever end up with an inconsistent corrupted index. So if a machine crashes, you should be able to start back up. Your index should still work, but you may have lost documents. So to not lose documents, you have to have a transaction log, which can then replay the updates that were lost in the crash. The transaction log also gives us the ability to do real-time get, which means we can ask for a document. You can't search for it, but you can ask for a document by ID that has been added to the system but is not yet viewable by a searcher. So that lets you do like NoSQL type operations. And the other thing the update log gives us is the ability to buffer updates. So we can buffer updates in the transaction log and not add them to the index. And that's important for this case of catching up. So the first thing a replica does when it comes up, it realizes it's not the leader, it has to recover from the leader, is it starts buffering updates from the leader into its transaction log. So those are gonna keep accumulating in the transaction log while it does the rest of this recovery process. The next thing the replica does is publish to Zookeeper that its current status is recovering. This is so that like other searchers know they should skip that node. They only want to search active nodes that are up to date. It waits for the leader to see that recovering state because when a leader sees a recovering state, it knows to forward documents to that replica. So we ensure that the documents are coming from the leader to the replica and that we're buffering those documents. After that, the first thing we try to do is what's called a peer sync. A peer sync is like a quick way to catch up with the leader. It basically pings the leader and says, give me your last 100 updates, and compares it to the replica's last 100 updates, and tries to see if there's an overlap. This was one of the problems, one of the areas we had trouble with, that we basically used this kind of last 100-day update window to determine if a replica was out of sync, and what we found was the way our update chain works, updates could be so out of order that it could look like there wasn't an overlapping window, and you could get the wrong result. You would think you were up to date when you weren't. So very recently, we actually added a fingerprint where you do a hash on all the versions in that segment so that you can really say, like, does this match, rather than just the sliding window. That was like one of the last reasons that replicas could fairly easily get out of sync. And since we fixed that, replicas getting out of sync has mostly gone away. So the first thing we try is this peer sync, and basically what that does is if you're only off by 100 updates with the leader, is it just trades those updates. And so it's very fast. If it finds that you're off by more than 100 updates, then it kicks in a full recovery. And the full recovery uses the old index replication to pull over the entire index. It first will send a commit to the leader, because a commit on the leader is what will actually make sure all the segments are written out on the leader, and when you do that replication, you're going to get the index up to that commit point. So we started buffering documents first so that there's some overlap. There's going to be some documents that are buffered that were also in that commit point, and that ensures that you don't lose anything. Once we actually replicate the whole index, we replay those buffered documents on top. The couple that might overlap will basically be a no-op, and then it will replay the rest until it catches up. Once it's replayed all those documents, it's actually caught up with the leader. It's going to publish active. Now other searchers will see it, and they'll be able to start searching it. Everything's in sync. It's kind of like a simplified version of that. It really does work, and the code is pretty much the same as I first wrote it, but there's lots of little gotchas and tweaks and hardening we had to do, and little steps in there. It's all actually pretty solid right now, but it took a while to get there. So that's kind of the easier case too. So that's when a replica goes down. That has to happen when the cluster starts up. When a replica dies and comes back, that has to happen. So another failure case, the replica is partitioned. This was a case that we punted on in the early days. So how we tried to deal with this initially was anytime a leader tries to send updates to a replica, if that update doesn't make it to the replica, the leader would try to ask that replica to recover, because it knows that, hey, it didn't get one of my updates while the other replicas took it. That replica is now behind. Something must be going wrong there. Tell it to put itself in a recovery state. The problem with that is that if the leader couldn't contact the replica for some reason, due to a partition, due to whatever reason it couldn't talk to it, it couldn't tell it to go, then it wouldn't go into recovery, And meanwhile, the replica might actually be answering other queries and not know that it needs to be in recovery. So Tim Potter actually came along later and added what's called leader-initiated recovery. In this case, when a leader can't send a document to a replica, it will, I think, still first try to tell that replica, hey, you missed an update, go into recovery. But if that fails, it will actually go to Zookeeper and register a special node that says, hey, that replica is out of date, it's messed up, it needs to recover. And then the replica itself can see that. As long as it can still talk to Zookeeper, it can tell that it needs to enter a recovery mode, either when it starts up next time or in other cases. It can flag itself and say, hey, before I actually go active or anything, I need to make sure I recover. And if the replica can't talk to Zookeeper, Zookeeper's kind of the arbitrator of what's live and what's queried. So if it can't talk to Zookeeper, it's considered dead anyway. So we actually had some bugs when we first had this. We had some issues where the leader could the leader itself could be put in replica, leader-initiated recovery. We had to use some atomic calls to Zookeeper, multiple calls at the same time, to ensure that only the exact leader in Zookeeper at this very second could put anyone in leader-initiated recovery. Otherwise, you could end up with these cases where every replica was in leader-initiated recovery. You couldn't start your cluster without manually going into Zookeeper and clearing that status. But through a bunch of people working through a bunch of Zookeeper stuff, we finally got all that to work pretty well. Okay, so the hardest case, this is actually, I think, the fewest people kind of know about this code. I never really see it touched, and not many other people work on it. So, but this is the leader recovery. When a leader goes down, things are a little more complicated. You can't just come back and try to sync up with the new leader. When a leader goes down, the whole cluster can be out of whack because some updates may have made it to some replicas and not others. So you have to do this kind of sync process. And the first thing you have to do is figure out who the best leader is. Presumably one of the replicas, after a leader goes down, is going to have the most up-to-date documents, is going to be ahead. So we have to figure who that is. And so the basic little dance that's done is everybody is kind of getting in line to be the leader in Zookeeper. So the first guy in line says, okay, I'm the potential leader. Let's see if I can be the leader. The first thing he does is check, was the last state that I published to Zookeeper active? If the last state was not active, then that node, we can't be sure that node is up to date, right? If its last state was recovering, then it's obviously not up to date. So the first thing it does is say, was my last state published active? If it was, I can still try to be the leader. If that happens, then it tries to peer sync with its entire shard, which basically says, hey, give me the last 100 updates from every shard. Try to see if I'm ahead. The only way it passes that peer sync is if it actually has more recent documents than any other replica. If it doesn't have more recent documents, if it fails against any other replica because they have more recent documents, it'll say, okay, I can't be the leader. It'll get out of line and go to the back of the line. The next guy in line will try. If that peer sync does succeed, then, so if that peer sync with the shard does succeed, then we try to peer sync from the replicas to the leader. So now, if the peer sync succeeds, we know we're on the leader that's the furthest ahead, but the other replicas may be missing documents. So we ask all the other replicas to peer sync from what looks like the current leader, and if they're only off by less than 100 documents, they pick up those documents and they catch up. If the peer sync fails from the replica to the leader in any case, then we ask those replicas to do a full recovery. So that means they were off by more than 100 updates. They just copy the whole index from the leader. So you kind of have this little dance as everybody tries to be the leader. And in some cases, nobody thinks they can be the leader. And that's kind of currently one of the limitations of the system. So the leader election forward progress stall. I don't think that this actually happens super commonly. At Cloudera Search, in the early days, we did start seeing it quite a bit. In most cases, you end up seeing this because of tuning issues. So what happens is if every replica in the shard gets disconnected from Zookeeper at the same time, then all of the last published states are going to be not active. They're all going to enter recovery at the same time. None of them are going to think they can be the leader. So basically, if this happens, if for some reason, like you get an out-of-memory exception on all of your nodes at the same time and they lose their connection to Zookeeper, then all of the replicas will keep going around this dance saying, hey, my last published state wasn't active, my last published state wasn't active, I can't be leader, I can't be leader, and we're kind of stuck. So why does this happen, and why are we trying to be so careful with protecting everybody's data in this way? And a lot of it is, initially, we didn't put the burden on the user, like many systems, for a variety of technical reasons initially. We didn't put the burden on the user to say, when they add an update, like, how many replicas does this have to hit for you to be satisfied? Because we didn't do that, then our kind of promise is, if you add an update, no matter how many replicas it gets to, we're going to try to protect your data and not lose it at all costs. So if you add an update and it only made it to 1 replica out of the 4, or it only made it to the leader and it didn't make it to any replicas, then we still try to do our best with this whole system to not lose any data. And so in the case where we kind of give up and we say nobody should be the leader, that's us basically saying we can't properly figure out who the leader is in a confident way with the current system. You should manually jump in and make sure all your replicas participate in a new election and you don't lose any data. It's really annoying in a production system to have this case happen, though, and with the idea that you need to manually jump in. So it's something that we have to kind of get rid of. So there is currently, because this did start popping up a little more, there is a new API that actually forces a leader. So in the past, to get out of this situation, you had to actually restart the whole shard and force a new election. There is a force leader API now where you can actually just trigger a new leader election and get out of this, but it still takes manual intervention. So basically, the system still has to change. And part of the reason that we didn't do this originally, where the user can say, hey, for this update, I need it to hit this many replicas to be considered a success, is that if it doesn't hit that many replicas, it's very hard for us to roll back and maintain data integrity. If the document only makes it to do 2 replicas, we don't really have a transactional system where we could say, hey, roll that update back from the 2 replicas because it was supposed to hit 3 and it didn't. So you're in this weird situation where you added data, you said I needed to have a replication factor of 3, it was only successful on 2 replicas, the update comes back and maybe we say it failed, but it didn't fail, it's actually in the cluster. So it's kind of an annoying problem that we don't have a great solution for yet, we're gonna kind of have to think about. You kind of face that problem as it is when you add an update. If you add an update and you get a fail where like the leader crashed, you actually don't know in that case whether the update's in the system or not either. It may be in, the leader may have crashed just before it could send the response, or it may have crashed before it actually added the update. So we do have cases where you're in a similar boat where it's on the user to figure out, oh, did the update make it into some replicas and not others? But I'm hoping there's some things we can do that are better. Because what we really have to do to get out of this boat where we're trying to protect data at all costs is put the onus on the user to say what the replication factor is, and then we don't have to try so hard to protect all the data, because what we can say is, oh, well, if you didn't want to lose data, use a replication factor for how many replicas you have. If you use a minimum replication factor of 4, that means that the update is going to be on all 4 of your replicas, and no matter what happens, it's likely to not be lost because it's on all those replicas. It's not just on 1. So let's see. So the basic idea is that there's some short-term improvements we can make to this. I've got a couple JIRA issues about it, and there's the more long-term thing. We do actually have that minimum replication update parameter now. You can use it. I think Tim Potter added that as well. You can send an update and say, I want to make sure this makes it on this many replicas. It doesn't fail if it doesn't succeed, though, partly because of that problem I just talked about. It actually comes back with a flag in the response that says, oh, we didn't achieve the replication factor that you asked for, and you have to look at that flag and adjust. So what we want to do is make that more of a hard fail. We want to think about what we can do to make it a little easier on the user when that does fail and the update is kind of in the system but not at the level of replication that you wanted. We kind of have to think through exactly how we want to deal with that case. So the short-term thing that I'm looking at is Solr 7065. There is at least one case where we can not stall on this leader election thing, where everyone doesn't think they should be the leader. What we can do is say, well, if every replica in the shard is participating in the election, who cares if anyone was last published was not active. Who cares if we think anyone's valid to be the leader or not? If every replica is participating in the election, all the data is there. You're not going to lose everything. So that's an issue that's like partway done. I know Mike Drobe is done a little work to help me try to finish it. But the basic idea is to say, hey, if every replica is participating in their election, don't worry about let anyone become the leader, because the way the dance works is the guy who's the most ahead is going to win. He's going to sync with everyone else and trade data, and you're not going to lose everything. That doesn't take care of the case, though, where you don't have all the replicas participating in the election. Say one of the replicas dies and it's not coming back for like a week, then you still have this problem. So what I would like to eventually get to is Solr 7034, where we take out all of this extra protection, where we're trying not to lose data no matter what, even if the data didn't make it to a single replica. And we can maybe keep some of that code. We want to still try to be somewhat careful, but we can much more put it on the user and say, hey, if we lost data, it's just because you didn't choose a high enough replication factor. And if you have data you don't care so much about, then you could set like a 1 or 0 replication factor, kind of the fire and forget type mode. And if you have data that you really care about and you don't want to lose, you can set a replication factor equal to the number of replicas you have. And that guarantees that any time the system says we accepted your data and it met its replication factor, you're not going to lose it because it's on. Well, you're not likely to lose it unless you lose all of your replicas. But presumably you have enough replicas to handle some loss. So that's most of the fault tolerance that's built in. It really is spread across like 3 classes: that recovery strategy class, the sync strategy class, and there's one called election context. So like those 3 classes, you can scan them and get a pretty good idea of how all of the fault tolerance in recovery works. Some of it is a little complicated or kind of touches other parts, but like the core logic is all in that. So it would be great if other people started digging into that. There really hasn't been many other eyes on that, especially the leader sync up algorithm. There hasn't been a lot of eyes or improvement or study of that, so I'm kind of trying to draw some more people into it. It's worked surprisingly well so far, but yeah, we've got to do something better. Another interesting part of all this is handling like full cluster shutdowns in startups. That's another reason we kind of tried to be so careful with your data. I was really worried initially about like an old replica showing back up into the leader election and becoming the leader and kind of taking over. We need to make sure at the beginning when you start up the cluster, you're not necessarily starting every single node at the same time. So we have to be careful that everybody participates in the election. If you have the election before the replica 3 and 4 start up and only replica 1 and 2 participate in the election, then it's a big problem. So we have a lot of issues with this type of thing where like when you start up and you shut down, it's hard for us to necessarily tell. Because we used to be considered a web app. There's no like cluster shutdown command. The way you shut down is you individually go to each web app and you shut it down. And so we don't really know the difference between that and you're turning off a couple replicas. So we basically have to be extra careful. So like when you start up, if all the replicas in a shard are not participating in the election, we'll wait for 3 minutes until we see every replica that we expect. And when you're shutting down, we have weird effects like when you shut down, we will actually stop serving requests before we pull out of Zookeeper. And it's actually been hard to fix that when we're a web app. We may actually be able to fix it now. But what that means is that the node can still look live as it's shutting down. And that can end up absorbing or slowing down a lot of traffic. That node can become hot as it keeps trying to get hit, but it's not actually serving requests. It can kind of act like sticky on shutdown. And so what we really need to get to is like actual cluster commands where you can send a cluster command that says I'm shutting down, and we can actually like pull those nodes out of Zookeeper before they literally start shutting down and can't serve requests, and you have much smoother things. So that's kind of a little unrelated to the rest of this stuff, but another thing we need to work on. And yeah, so now, any questions? That's pretty much it. Scott?
I got one. So on the slide you were talking about where the leader might shut down and then the other nodes may have to elect leader in its absence. What happens when the original comes back up if it has some documents that never
So though if it had documents that never went out, they wouldn't have been ACT. So the document, when you send in an update, it's not acknowledged until the leader has sent the document to all the replicas and they've received it. So you can pretty much count on if it said that it received the document, then all the replicas have it, or those replicas are going to be put into recovery mode. Go ahead.
Is there a rollback or rollforward kind of thinking there when kind of the leader comes back and when it recovers?
Like a rollback? What do you mean?
From the log file, from the transaction log file.
Yeah, so the question is like when a new leader comes up, is there like an ability to roll back using the transaction log? So we can't easily roll back. The way the whole system is built now, rolling back is very difficult. So Lucene and Solr don't have like real transactions. They kind of have this atomic transaction with the commit, but it's not like a database transaction where it's like prepared and you can either then finalize it or roll it back. And so, yeah, I don't know. I've talked to Yannick about it some. I don't remember all the details, but any kind of rollback is really difficult. So I'm not sure how we're going to handle the case where like we want to fail an update and not have it be in the system at all. It's really still an open question. But it's definitely where we need to get to, I think. Go ahead.
Mark, the 100 limit on the peer sync is configurable now.
Right.
I think Rom did that, but I've seen people basically set it to tens of thousands to avoid full index recovery happening. But I've heard there's like an issue with that being too big.
Yeah, so Yannick always pushed back on raising it above 100. It really depends on how big your documents is. I think the main concern is the amount of RAM it's going to take. So if you have a ton of RAM, I think that's fine. And then peer sync doesn't stream yet. So when you're sending all those documents, yeah, it's going to take a lot of memory. But yeah, if you have the hardware, you can raise that a lot. 100 updates really isn't much. You will find actually that peer sync doesn't work that often. If you're indexing with any speed and something dies, the chances one of the replicas is off only by 100 documents is fairly low. So personally, I would raise it a lot, especially if you have tiny documents. Any other questions? Go ahead. So the question is, when a replica gets out of sync, is there a way to know about it? There's not actually a currently easy way. Usually people notice because you do a search and you get a number of results and you're not changing the index, and you do a search again and the number changes, and they keep searching and getting a different result set back, and that's because it's cycling through the replicas and one of them's out of sync. We had talked about Cloudera, though no one ever got to it, trying to make a tool that could kind of manually go in and check and look. But the system itself cannot really detect that, nor easily recover from it. We just try our best to fix the issues that get you in that situation. And that's, I think that's just because it's really challenging to have the system be able to kind of detect and recover from it. It would be great if we get there, but currently it's a ways out, I think, before it can do that. Scott?
Do you have any thoughts on short-circuiting some of the like leader election code for shards that only have a single replica?
Yeah, I mean, we've spent so little time focusing on like kind of like corner cases or specific scenarios like that, but yeah, I haven't thought about it a lot, but there is probably some things you could do to make that better. I'm hoping that we can actually short circuit and gut a lot of that and make it faster just when we move over to forcing the user to specify the replication factor. I think there's just a lot we do that where we're desperately trying to make sure that even if you sent a document and it's only on 1 or 2 nodes, we're just desperately trying to make sure we don't lose that data, and we can subtract, I think, a lot of the complication when we're not doing that. Any other questions?
Yeah, so I take it this addresses data that's written and maybe lost during the write process. Does this process address data that is lost, hasn't been read in years, for example, on disk?
Yeah, so it doesn't really do that. Lucene itself has worked on that, though. Like, it will actually, I think it's a CRC32. It does a checksum on all of the index files now. And so when it's reading them, it will compare to the checksum it originally wrote. And so it will actually, Lucene itself will actually kind of flag corruption that used to be pretty much silent, or you might get a random error. Now it can generally tell if cosmic rays flip some bits and the checksums for that file don't match. And when you open a reader on that, you'll see. The only way to deal with that really is to have backups, I guess, at this point. Once you get that corruption, you're kind of done. But yeah, backups in general are still really important, because while you do have replicas, it tends to be that if you get an issue in one of your leaders, that tends to go out to the replicas pretty quick too. It's not often the case that one of your replicas gets messed up and the others don't. Because what can happen is you'll get a full index recovery or something that just moves the broken leader index to the replicas or something. So yeah, backups are still really important, I think. Go ahead.
What's your experience been with Zookeeper itself? Have you run into, like, 5-6 years that you've been using Zookeeper, the issues and bugs in SolrCloud, have you done activity in Zookeeper failure?
Yeah, Zookeeper is like really, really solid. We almost never run into issues with it. I see bugs reported against it, and I see things that are fixed, but I've never found them myself working with SolrCloud. The main issues we've had are kind of our own bugs in using Zookeeper, not bugs in Zookeeper itself. It can be a tricky user API to get exactly right with everything that we're doing, and there's definitely been a long hardening process in that. But Zookeeper itself is really simple, just runs, and it's pretty solid.
So you mentioned the replication factor. Say I have a shard, like my cluster size is 2 shards, 4 replicas each, and when I add documents, my replication factor is 2, right? So whichever shard it goes to, at least 2 of the 4 will have the document. But when I query time, how does the system determine that the document being searched for is on these 2 and not the other 2 replicas? So I'll surface the result from here and not the other one.
They're from different shards?
Well, so one document goes to shard 1, replication factor of 2.
Right.
Right? So it's on 2 out of the 4 replicas on that shard.
Right.
When I query, that document is an eligible document for himself. But is the query going to go to all 4 replicas to find this document?
Well, so it's when you say a replication factor of 2, that's the minimum. It's still going to try to send it to all 4. And if it fails sending it to any of them, it's still going to put that into recovery. It's just going to say, if a couple of those died while we were adding the document and we can only make it to 1, then fail it. Whereas the current system would say, oh no, 1 got it. It succeeded.
Okay, understood.
Go ahead, one more. Say that, are we using a chaos monkey type test? I can only kind of hear, but I think the question is, are we using like a chaos? We do actually have a couple chaos monkey unit tests that spin up clusters and randomly kill nodes, either randomly kill leaders or randomly kill replicas. And we actually wrote that very early. And it actually, we have to look at it again, but we actually got it passing really consistently where it could pass hundreds of cases in a row. It was actually finding issues that we've been fixing for the last 5 years ago, but it's taken us that long to slowly work through all of them. It actually, it's a really good test. The problem is at the beginning it was finding lots and lots of things, and you kind of have to just slowly work your way through it. You know, every now and then when we're not running it all the time or paying attention, some things get introduced that maybe start it failing again. But yeah, we have some good testing on that. There always could be more and better, but our Chaos Monkey tests are really the only reason this probably even closely works. They find a lot of stuff. I think we're out of time, but thank you very much.